Okay. So to start the seminar series of course, today we have Yanting Teng. She did her undergraduate at University of Illinois, and now she's a grad student at Harvard University, and she will talk about learning topological states from measurements using variational tensor network tomography. Please, Yanting.
Thank you, Mark, for the introduction. Yeah, so my name is Yanting. Today I'll be talking about this work of learning topological states using this approach. And thanks for the invitation for me to talk about it. And just a minor correction, I actually graduated about 3 weeks ago. But I mean, no worries. It's very recent. It was not online at all. But I appreciate you looking into it. Yeah, so I'm super happy to take questions during the talk. So feel free to interrupt. So this is a short talk, so I'm just gonna jump straight into it of introducing what kind of states we're trying to learn. So we're looking at quantum spin models, and here are spin-and-a-half operators. And okay, we could imagine there's a classical configuration for spin, spin up, spin down. But generally, this is a quantum model, and to solve these models exactly, we need to diagonalize exponential large matrices. And there's a lot of work people have done in condensed matter physics, where I did half of my PhD on, more or less. And so it depends on these, the models look simple, but depends on these couplings here. The ground states can be highly non-trivial. And when the ground states are very quantum, there are these states called quantum spin liquids. And very coarsely, we could classify quantum spin liquids into gapped states versus gapless states. Gapless states are more complicated, but here it's kind of like just think about what other gaps look like. But in this talk, we're going to be focusing on gapped quantum spin liquids, which we say that they have topological order. And these are kind of states we're going to be looking at. And in particular, we're going to look at the two topological order because it's very simple. And okay, I'm going to keep going. And so these states have long-range entanglement. This is manifested by topological entanglement entropy, which is the constant correction to the area law in two-dimensional models. And so if we have a ground state with the topological order, then the excitations are very interesting. They have anionic statistics, meaning that the excitations can acquire very interesting phases when particles are braiding around each other. So this is a cartoon of Takeda Topological model where there are E anyons, M anyons, and then the bound state is also an anion. It's an epsilon anion. So when we wind E anion around the M anion, it picks up a minus sign. And these states are not just fundamentally interesting because of these properties. It's also very practically relevant given very strong interest in fault-tolerant quantum computing with surface code, which is open boundary condition for the Tor code. And there's a lot of research in quantum error corrections using surface code states as logicals, and very impressive recent works from industry. So to look at where these states come from, just a quick refresher of the Topological model. So these are the Hamiltonian terms in the Topological model. So these are spin operators, spin-and-a-half operators, and they live on the edges of the square lattice. These are the white squares. And so there's a plaquette terms, a product of the sigma z, and then star term, product of sigma x. So this model is exactly solvable, showed by Kitaev, and the ground state is a superposition in the z basis. It's a superposition of different terms. So here, the blue line representing one spin configuration versus the other is the other configuration. So because it's a topological state, it's long-range entangled. In any local basis transformation, the state is always going to look very entangled like this. And it might look very random, but there is a lot of structure in the state. So the model might seem very contrived by Kitaev, but the state is actually the same class of state arriving from Z2 gauge theory. So we say it's emergent topological order. So how do we see that is we can imagine adding perturbations to the Hamiltonian. So we can add sigma x or sigma z local field perturbations. And it's very remarkable that the torical state remain pretty stable with large perturbations. So it's a stable phase of matter that's a phase in the emergent Z2 gauge theory. And this is remarkable that it's the same described, but this theory people studied 50 years ago. And so in this framework, the original spin operator, it can be promoted to gauge fields. And the original E excitations on the vertex become the matter field excitations in the gauge theory. And then the plaquette excitation, M excitation become the Weisel flux excitation of the gauge fields. And in the rest of the talk, this order is going to be what we're going to be learning. And in particular, in the torical model, for instance, or I guess surface code, if we have two states that are both topological and they're different states, then because these are topological states, they cannot be distinguished by local operators. Therefore, the information is really encoded in the global wave function. And so the two examples we're going to be looking at in particular for the rest of the talk is first going to be the surface code that we just talked about, and then the other is going to be the quantum spin liquid observed in the Rydberg atom array experiments 3 years ago. And this phase has the same order as the torical model. Okay. And this talk is going to be, we're going to try to see if we can do quantum state tomography on these states. Okay, so the high-level intuitions of state tomography, I'm going to explain like this first. So imagine we're trying to learn dogs and cats. And so I'm imagining that I know what concept of dog and cat is. And what I'm really thinking is there's lots of pictures of dogs, lots of pictures of cats, and they're kind of like separated. So we have a classical distribution, maybe parameterizing different kind of dogs, and then the different distribution parameterizing different kind of cats. And we're trying to learn the underlying distribution that's generating these instances of dogs and cats. In quantum state tomography, it's similar in spirit in that when we take a measurement of the state, we're seeing different spin configurations. And this is actually very precise because these configurations are generated from precisely distributions defined by the wave function. And of course, there's difference from the analogy in that we can measure the state in different bases or after different unitary transformation. And moreover, we don't have the state is not parameterized by a classical distribution, it's parameterized by a state, but then we get a classical distribution when we're measuring. So there are differences, but at the end of the day, the goal here is imagine we have a state and then we're taking measurements and we know how we take a measurement from different angle. And we want to just reconstruct the original state that's giving us these measurements. Okay, that's pretty clear. And so in particular, more precisely, the way we look at the system from different angle is by using different measurement schemes. For instance, we could just do computational measurements and maybe just rotate the x basis. So that's global xz. Or we could do local computational z and then rotation to x. So this random xz. We could also xyz, that would be poly measurements. Or we could do a global unitary, Clifford unitary, and then measure for other kind of schemes. So once we choose a measurement scheme, then we're going to choose how we're going to process this data. And here we are choosing our favorite protocol. And then finally, once we process these data, we inferred a state for these measurements, then we can evaluate. For the rest of the talk, we're going to be looking at just poly measurements. And we're only looking at poly xz measurements, which I'll explain why in the next slide. But so we're going to be looking at just poly measurements because they're the most precise kind of measurements that we can do experimentally. And then we're restricting ourselves to pure states for the rest of this talk. So we're looking at fidelity for evaluation. Okay, so why do we pick XZ measurements here? So there are some motivation coming from the experiments. In the Rydberg atom array experiments, they are very easy to do local X and local Z measurements. And moreover, the states we're looking at, we have restricted the Hamiltonian to be real. And therefore, we guarantee that the state is actually a real state. So there's no, you can have a global phase, but there's no relative complex phase in the wave function, in the wave function amplitudes. So basically, we're guaranteeing that by only measuring X and Z poly measurements, these measurements are tomographically complete on the set of real pure states that's our target states. That's why we chose these measurements to be more efficient. And so just some high-level intuition on why this is true is that, so very simply, if we're just measuring computational basis, given infinite measurements, then we can determine the amplitudes, absolute amplitude of the state. And then if we imagine changing basis of some spin to X basis, then we can extract the relative sign of the second bit in the amplitudes. And then if we change the basis in the first qubit, then we can extract relative sign of the first qubit. And therefore, we could determine all of the signs and amplitude of the state. And of course, this is a infinite measurement intuition. So given infinite measurements, we guarantee that we're going to recover the full state, tomography complete, and how many samples we're going to discuss for our protocol. We're going to discuss that. Okay. So that's measurements and protocol. And okay, so now I'm going to talk about protocol. So given the measurements that I just described, the random, let's say we choose random X, random Z measurements, and we have n snapshots, then the protocol is that we're assuming a tensor network model. And then we know what how we measure the system. So we feed that in, and we also feed in the measurement outcome. And we minimize a loss function. So here, B is the measurement outcome. So B is the bit string 0, 1 measurements, and then U are these the way we measure the system. And then psi is the model dependent on the tensors A. And A is the tensors that we want to find given the loss function. So here, the first piece is the maximum likelihood estimation cost function. And that's very established in quantum state tomography. And here, because we're doing randomized measurements, we could actually add an additional piece, which we call classical shadow regularization. It's basically because if we have randomized measurements, we know from classical shadows that we can estimate local operators very well because we're doing Pauli measurements. So we could estimate some observables, then we could just make sure that our model agrees with whatever classical shadow tells us about. And we could add that optionally with some hyperparameter beta. And so this is our loss function, and we can just do gradient descent and find the tensor that parameterize the tensor network. And once we have that, we have the full state, and then we can compute anything. So we could first check that fidelity is good. And then once we have good fidelity, we can compute entangled entropy or non-local observables. That would be hard to estimate given Pauli shadow. Okay, so that's the protocol. If there are no questions, I'll move on to the results and for.
I have a question, if that's
Mhm.
okay.
Yeah. For sure.
So you're kind of, it seems to me like for this maximum likelihood estimation, you're assuming a tensor network structure and kind of finding the tensor network that best fits your measurements.
Yeah.
But I guess for things like the toric code, this is very long range entangled. And so like if the state you want ultimately doesn't have a good tensor network representation, like I guess how do you deal with that?
Oh yeah. Definitely. So this is a very good and tricky question. So in the rest of the talk, we use MPS, so matrix product states in our numerical results. So you're totally right that MPS is, so if you do, what we do is we do a 2D snake path, and then if you do that, then the bound dimension of MPS will blow up exponentially with the size of the Y. And so in the numerics, in the system we look at, we do restrict the Y axis. So we're still looking at topological states, but the states we're looking at is just small in one axis. And so for the rest of the numerical results with MPS, this is still okay. And of course, for a state that's both large and wide, then you would want to use a different tensor, maybe 2D tensor network ansatz. That's for sure. And here we're kind of like taking the inspiration from DMRG, where people just do like snake path for 2D system, as pushing it as hard as they can and seeing how far it goes. But I totally agree that we will want to use 2D ansatz.
But I guess my question was more like, even like, say for instance, like, you want to, do tomography on like a Haar random state, which is, I mean, any like tensor network approximation you would try to make would just, I mean, it would just be, you'd have a huge number of parameters. So do you really, this works like most optimally for things that are closest to a tensor network representation?
So yeah, because topological order states satisfy area law, here we know that the entanglement is bounded.
Okay.
Yeah, I think for random states, I totally wouldn't use a tensor network.
Okay, cool.
Yeah.
Thank you.
Yeah, no problem. Are there any other questions? Okay, we can have a discussion if there are no other questions. Okay, so how does it look overall? Just give an overview of like what I actually do in the numerics. It's pretty simple. So taking surface code Hamiltonian as an example. So here's surface code Hamiltonian that we saw before, some stabilizer terms, and there's perturbation, and the MPS ansatz, we're doing a snake path in this black line. And so all of the results in the paper and the rest of the talk are numerically simulated, are using numerically simulated data. So how do we simulate data? We could just do DMRG on the Hamiltonian, and we will get the target state that we assume is there, that we can just take measurements. We can sample the target MPS, then we can just generate the data. And of course, we don't feed the target MPS to the model. We only feed the data set that's measured by from simulation. So we can look at different measurement schemes, different system size. Yeah, and so once we have a data set, then we could choose what kind of model we want. So we can tune the bound dimension, and then we could choose how much data we're gonna feed to the model, and then different regularization strength beta. And then we can just minimize the loss function, and we get the trained MPS out, and then we can just compare the two MPS. So that's supported by a lot of the hard work of other people's code base, which is these. So what do the results look like? So for 3x3 surface code that showed on the previous slide. So here we're looking at number of samples, which is the data set size. We feed it into the model on the x-axis, and then on the y-axis, we're looking at infidelity, which is just 1 minus fidelity. This is a log-log plot. And so overall, we're seeing that with more data, the model performs better with lower infidelity, which is good. And here the cross and dots correspond to the global fixed basis measurements versus random measurements. Both are XZ measurements. And so they both go down while global beats random here, which makes sense because global Z and global X measurements are just measuring the stabilizers directly. But the amazing thing is that random XZ measurements also succeed in terms of learning the states, just a little worse sample complexity. And that is pretty incredible. Just assuming that we know nothing about the states, we just made random XZ measurements, and from those measurements, we could reconstruct the state up to pretty high fidelity given these measurements. And here the color is regularization strength, beta. So light to darker is more regularization. And here we're seeing that with more regularization, the model performs even slightly better, even given the same set of data, which is very surprising to us because it's like, it's the same set of data and you just give them a different loss function. And then with more regularization for surface code, it performs better. What is the regularization we're using? So here's the regularization term. So it's from the data, we can estimate the stabilizers. So the operator we're using are the stabilizers in the surface code. And we can estimate it directly from the data. And then we just penalize the difference with auto norm. So this is estimated from classical shadows. Okay. So that's a toy model, 3x3 surface code. And now we're going to look at how this method scales. So as Henry brought up just now, that there's the issue of how much entanglement we have in the system. So here, because we're using MPS, we know that the ansatz will not be able to represent arbitrarily large entangled states. Therefore, here we kind of just fix the y-axis to be limited to test how well the method is working. And when we scale the system, we're scaling the x-axis. And we scale that up to 45 qubits. And so here is a similar plot of how infidelity improves with number of samples. And for larger system, it definitely requires more sample to achieve the same fidelity, but overall still pretty good. And then if we impose the condition that we want to require certain fidelity target, and here we require a local fidelity target to be a little less stringent, then we can look at the number of samples required to achieve a local fidelity threshold for different number of qubits. Overall, we see that with more qubits, there are more samples required, which makes sense, but the number of samples does not explode exponentially. So given that the ansatz we choose can parameterize the target state, then the sample complexity does not scale exponentially with number of qubits. And again, the color is same as before, with darker parameterizing regularization, with more regularization, fewer samples are needed. And the same for dot and cross are random measurements and global measurements. Global measurements perform overall better for surface code. Okay, so these are the results I would like to show for surface code. If there are no questions for these, in the next slide, in the next last few minutes, I'm just going to talk about the results for the spin liquid. So the Rydberg atom array, the Rydberg atoms can be modeled by a two-level system. So there's the ground state and there's a Rydberg excited state. And the Hamiltonian is basically like a transverse field easy model with a interaction range described by the Rydberg interactions. So this is where it gets interesting, which is the coupling interaction. So when depends on the laser parameters of the system, we can tune the interaction to be large within a radius. So if a atom is in the Rydberg state, then because of the strong interaction within a radius called blockade radius, then it costs a lot of energy on the order of V to excite another atom in the vicinity of a Rydberg state. And therefore, once we have a Rydberg state in the light circle, then this neighboring radius within 2A will always be in the ground, will most likely be in the ground state. And so because of the strong interaction, there is a spin liquid state arising given certain tuning parameter strength of delta and omega, describing the onside and transverse field terms. And then if we tune the parameter on the other side, then the state can be in the disordered state. And in general, disordered state, just by looking at snapshots, spin liquid state will just give random configurations. Like we saw in the Tor code, it's like a sum of different configurations, and it just looks pretty random. And in disordered state, it also looks pretty random. But these states are very different because spin liquid has topological order and it's long range entangled. Any excitations and disordered state is just a disordered spin configuration. It's more classical. And so very interestingly, this is figured out that the spin liquid phase exists in this model by mapping the Rydberg excitation onto a dimer in the link. So if we have a Rydberg atom here, then we can map a dimer here, and similarly here to here. And then we see that there's an emergent non-overlapping dimer configuration in the Kagame dimer model versus the original rubric atoms sitting on the Ruby lattice. And because in condensed matter physics, people have studied Kagame dimer models, and they know that there's probably going to be a spin liquid, and they map it backwards and figured out this is going to be a spin liquid state. Okay, so we're still using DMRG simulation as ground truth for same as before. So with the DMRG in these two parameters of the phase diagram, and we get the target state and we generate snapshots, and that's our data set, and we train a model there. So for both of these states, so we look at system size of 48 atoms. For both of these states, we see similar behavior. With more data, a model performs better, and that's great. And now, because we're not looking at stabilizer state anymore as the surface code, random and global are similar, and sometimes random outperform the global measurement schemes, which makes sense. Now we're not just directly measuring stabilizers as using the global scheme in the Turing code, in the surface code. And now here, so the cross is global, and then here circle is random with regularization. Sometimes regularization outperform no regularization for this order state, that's okay. And that's good. Oops. And for spin liquid, they kind of look similar, but with regularization, there are less outliers compared to with no regularization. And that's interesting, but it's not always regularization is better. Just to mention what we're using for regularization in this case, we're estimating all the polys supported on the subsystem, because now we don't know what the stabilizers are, so we don't know what are important operators, so we can only just kind of look at all of them in a subsystem. And so we chose the subsystem in a unit cell, and then we estimate all the polys supported on the subsystem that can be estimated by using XZ shadow. And here is the result of with regularization in these darker dots. Okay, so once we have a model trained state that it has high fidelity, then we can predict any quantities. So just to give an example of what we can look at different product of polys that were studied in previous works by Ruby and Ashray, and that's how they believe that they have a spin liquid in the original experimental paper. And so they can directly measure these FM operators, and we can just verify, we could in principle verify with the experiments that what our model prediction is, and it converges pretty quickly to the target that we assume one can measure. And here for a larger poly, it converges a little slowly, but it eventually also converge. And so this P logical is product of like more larger polys across the system. And so these are what the experiments can in principle measure directly, and we can just confirm, verify that our model indeed give the observer they're expecting. And additionally, we could also compute entanglement entropy, which is something you cannot, they cannot directly measure in the experiments. And we see that with more samples. So the color is samples here. With more samples, the entanglement entropy converge to the ground truth, which is these empty circles. And so that's something we can predict. And so finally, just let me comment on the kind of scaling we've been seeing over and over again, which is a polynomial scaling of the infidelity with number of samples. Here for surface code, alpha is 1, so it's polynomial. So the fidelity gets better with samples in the polynomial scaling. So with collaborators, we're able to prove that such polynomial scaling is expected with a concentration inequality. Here the error is scales with number of qubits and bond dimension of the model we're using squared and divided by the number of samples and confidence probability delta. Okay, so with that, it's 30 minutes. I just summarize a little bit. So here in this work, we try to learn topological states. These are 2D states, hard to learn in general from measurements, poly measurements, poly-XZ measurements in particular. And we use this MLE plus shadow regularization with a tensor network here, MPS for the numerics prior. And we showed that the method scales, the method is able to learn these states up to high fidelity with reasonable number of samples. And we proved random XZ measurements are great measurements for our purpose. And we showed that how infidelity will scale with number of samples. And we looked at 2 states, surface code here and spin liquid. And there's a few directions, changing ansatz, improving optimization, and looking at other kind of fundamental particles, fermions. And yeah, I would just like to acknowledge my wonderful collaborators for this project. I learned a lot from Catherine. She worked on random XZ shadow, and Frederick Jens from Berlin, Ryan worked on the MLE's sample complexity part, and Ryan Severe, spin liquid, and so now we started the project together. Yeah, thank you so much for your attention, and I'm happy to take more questions and discuss with you.
Okay, Henry, go ahead.
Hi.
Hi, yeah, so very nice talk. Thank
you.
you. I have some questions about the shadow regularization you used. So can you go to the where you first described it in terms of the stabilizers?
Mm-hmm. Let's see. So that's surface code here.
Yeah, so these are, I guess, so I think about things in terms of like a toric code. So for that, would these just be your plaquette and star operators?
Mm-hmm.
And in terms of actually estimate, so you might have mentioned this and I just missed it, but this will also, like, the complexity for getting a good regularization, this depends on like just kind of the normal shadow complexity.
Mm-hmm. Yeah, exactly.
And so is this, I guess, a limiting, or to what extent is this a limiting factor?
It's not a limiting factor. It actually helps for small amount of samples. So the sample complexity for estimating the stabilizers very well, just it generally scales exponentially with the size of the operator, but we're using a small operator. So for surface code, it's 4 poly, and that's not a very large poly. So we think we can just estimate them pretty well. Yeah, so I don't think that's a limiting factor. I mean, okay, so it's a limiting factor in the sense that in the spin liquid, in the Rydberg atom array, we don't think these are the best polys to use, but we also don't know what else to use. I think some larger poly would be beneficial, but that would be more expensive to estimate. So in that sense, maybe like if we want to regularize, we have to believe that a small polys are useful, which we don't generally know. And here we're just trying things. But for surface code, it's not a limitation.
Okay. Okay, but if I was, I guess, interested in like doing, say I had like, I wanted to do like use like a ribbon operator. This is something that like goes around the full system. This would be a problem then.
Yeah.
Okay.
That would be hard.
Okay, thank you.
Mm-hmm.
Hi, Yanting, thank you very much. I have a couple of questions. So one is, if I was to do this on a machine today with say 100,000 measurements, that's a long time. what's when you've actually done this on the machine, what sort of sample size have you had to get, and what sort of fidelities you had to recover?
So you mean experimentally?
Yeah.
I'm not very up to date on what's the most recent speed for taking snapshots. My impression is something like 10,000, 20,000 shouldn't be too hard, but I can't say for sure, unfortunately.
Over 20 hours.
Yeah.
Yeah. Okay.
Maybe it'll take a day, or that's a wild guess. So.
Yeah. Okay. And my second question is the 1 over n scaling. How do you beat statistics? How do you beat square root n statistics?
Yeah, that's a great question. So yeah, in the surface code, we saw a alpha equals to 1 scaling.
Yeah.
And you know, the thing we can prove is square root, and we're seeing better than square root scaling. And that we don't have rigorous explanation still. We think it's because of the stabilizerness in the target states. You know, if you can estimate a lot of terms simultaneously, somehow you can beat the like square root. So we actually did some more. Sorry, I'm trying to find. I actually did some more numerics on that. So what did I mean by that? So here we're looking at GHZ state and the random state. So we're interpolating between, like, if we're choosing a state, we're interpolating how much of the stabilizer GHZ state we have and versus how much of random state we have. If we have a fully random state, so the lightest is the random state, then we're seeing the square root prediction that we predict in the theorem. But if we're we're including more and more GHZ state, then we recover like this -1 scaling again, which is why we think because stabilizer states, it's easier to learn basically that we can somehow beat the square root, but we don't have a good explanation of the -1 power still.
Okay, right. Interesting. Thank you.
Yeah. Thanks for the interesting question.
Any other questions?
Yeah, I guess, do you have an idea of how noisy measurements would affect this learning scheme?
Yeah, some noise in the poly measurements. Unfortunately, I don't. Yeah, that's another great question. Yeah, we didn't look at noise in this work. Yeah, if anyone have thoughts on how we could think about that, I would love to chat.
Yeah, the noise is one of the things that's obviously what you're thinking about. The noise is one of the things that makes VQE difficult, right? Trying to actually get to a minimum when you have error bars on measurements. It's one of the major complications.
Mm-hmm.
From the numeric side, it's probably not that hard to study noise. You know, you just inject noise onto your measurements.
You mean just run a simulation of the
Yeah.
of the whole process? Sure. Yeah.
Just to see what happens.
Just like noise in measurements, but still compute fidelity with the original target state. Yeah.
I'm just thinking from the point of view of trying to run a protocol like this on data from an actual device.
Yeah, right. That's the goal. For sure, that's a very important question to consider. Yeah.
I mean, you could Monte Carlo just white noise pretty easily.
Yeah.
But the correlated noise of the machines.
Yeah, I mean, that also certainly would depend. There's probably different types of noise that are affected differently.
Yeah.
Mm-hmm. Okay.
But I mean, you have some sort of noise model for your systems, right? So you have at least some information as to the correlations.
Mm.
Question from the Zoom people.
I have one question. So I guess it's kind of similar to the what we're talking about with the stabilizer. So if you were to not take the exact torque code state, but like go somewhere else on the phase diagram, but you're still in the same phase as the torque code. So at that point, like, have you tried to learn those states? So there, the stabilizers won't be. Well, yeah, your stabilizers won't be. You won't be at the plus one eigen states anymore, but still, like theoretically, all the same. Information theoretic quantities should be like roughly the same.
Yeah, totally. The states we look at is we look at the exact state, but these results are for perturbed states. So here HZ is these are perturbed states.
So what if you were to get closer to the, I don't know what the critical value of H is, but if you go there, what's the performance like?
That's a good question. I imagine that close to the phase boundary, it's going to be harder to learn because the state, I think the state will be more entangled. I may be wrong, but I think it's going to be more difficult to learn because of the entanglement. So there's probably we would have to use a larger bond dimension. And with larger bond dimension, it's actually harder to learn, which is expected. Yeah, but on the other side of the phase diagram, I don't think it's hard to learn because it's a trivial state or not entangled state. Yeah. But I mean, I guess here we looked at a relatively small region, not very deep to the phase boundary. But I guess my intuition is that if the bond dimension we choose is large enough, in principle, we could literally learn very close to the phase boundary. Just requires more samples. But how much quantitatively, I don't know. That's a great question. Yeah, if anyone had thoughts on that, I would be also curious to know.
Thank you again, Yanting.
Thank you so much for the interesting follow-up questions. Yeah.
Yeah, I have another question.
Go ahead.
If I have another question, if you mind. So, thank you for your talk. And on some of the questions, it was the prospect of simulating this on quantum devices has been brought up. Which ones do you think are the most promising? Digital devices or experimental implementations of this system, like the Kagome lattice with Rydberg atoms, or something else?
Yeah, I think for this method, it doesn't matter how the state is prepared, right? Because once there's a state, like if you can measure in local basis, this method works. But in terms of state preparation fidelity, my impression is that digital can achieve pretty high fidelity now, given very high fidelity 2-qubit gates and so on. So that would be promising. But the question is, like, if you prepare the state, you know exactly what the state is going to be, why would you do quantum state tomography? So I think it doesn't make sense to do quantum state tomography on the digitally prepared state because you can benchmark it differently. Versus analog, like the state preparation might be a little off, and that's exactly why we would want to do quantum state tomography in the first place, without having to measure all of the polys to fully characterize the state. So I think from that perspective, I would say analog states, like some kind of states we're trying to learn, like we don't fully know about what the state is. I think that would be the relevant states.
Thank you.
That answered the question. Yeah, but totally we have to look at noise Yeah. Thank you.
Close the recording.